Welcome to rankstudent.com, the site preferred by millions of students around the globe for digital education in science and technology. I'm Dr. Ahmed. I'll be your host for this brief review of the chapter on motion in a plane. If you're looking for historical examples for motion in a plane, it is said that the Mongols, who had conquered China in the 13th century, learned the use of the gunpowder from the Chinese. They would attach a small amount of gunpowder to the tip of the arrows and shoot them in the air. And these burning arrows, as it were, would make whistling sounds, and depending on the velocity, the sound would be different. And this sound was used for communication between various wings of their vast armies. A second example are the rockets used by the Mysore armies of 1799, the war against the British, or a goal scored by the Brazil soccer star Pelé in the World Cup match of 1958, or indeed a boundary scored by the India cricket star Tendulkar circa 2004. Now, strictly speaking, a cricket ball or a soccer ball or even a rocket or a whistling arrow may not travel in a plane, but it's a useful example if we were to disregard for a moment the motion in the third dimension. Then we have a great deal to learn from the motion of a soccer ball or a cricket ball. First, some definitions. Scalars and vectors, we have come across them in the past in the chapter on rectilinear motion. A scalar has magnitude but no direction. A vector has both magnitude and direction. Example, when you ride a bicycle on a country road, your speed may be constant at, say, 10 kilometers per hour, but your velocity is changing with every turn. This is illustrated in the diagram on the right-hand side, where I assume that you're bicycling from P to P1 at, say, a constant speed, but your velocity is changing from P to P1 because the tangent to the curve PP1 changes as you traverse the curve PP1, and the velocity is tangent to the curve at each of the points that you traverse. To be equal, two vectors must be equal both in magnitude and direction. Two vectors that are equal in magnitude but are different in direction are not equal. Again, going back to your example of riding a bike, your position vector changes moment to moment unless you're riding in a straight line. A few mathematical operations on a vector. If you multiply a vector by a number, let's say in this example lambda, what you do is to stretch the vector in the same direction. So the vector maintains its direction but is stretched. Its magnitude changes. Additions and subtractions of vectors are commutative. A plus b is the same as b plus a. When you subtract a vector by itself, you get the null vector, which is 0. Vector additions and subtractions are associative. For instance, a plus b plus c is the same as a plus b plus c. A vector in the xy plane can be resolved into its components along the x and y axis, represented here as a equals axi plus ayj. Similarly, a vector in xyz space can be resolved into a equals axi plus ayj plus azk, where I, j, k are unit vectors along x, y, and z axes. Vector addition and subtraction are fairly straightforward. If you have two vectors a and b and you add them up, then their components along the x and the y and the z axes add. A plus b would be equal to ax plus bxi plus bx plus byj plus cx plus cyk. the motion of a body in the xy plane, the position vector in general, designated by r, is given by xi plus yj. The velocity vector is v equals dr by dt and is tangent to the trajectory of the body. The important thing to remember is that the velocity is not in the same direction as the position vector. Here, going back to the diagram that we saw earlier, a body is moving from P to P1. At P, its position vector is r. At P1, the position vector is r1. When it moves from P to P1, the change in the position vector is delta r1. The velocity at point P, which is the limit of delta r1 or delta r divided by delta t, as delta t goes to 0, is tangent to the curve at point P. The magnitude of V is given by V is the square root of the components squares in the x and the y direction. V equals square root of Vx squared plus Vy squared. This type of addition we have come across in algebra. And the inclination of the vector V to the x-axis is given by tangent of theta equals Vy or Vx as illustrated in this diagram here. So the theta is the tangent inverse of Vy divided by Vx. When a body moves in the xy plane with uniform acceleration a, its position in the x and the y axes is given by Vx equals V0x plus Ax of t, that's as measured in the x direction, and a similar equation as measured in the y direction. In general, if the position of a body at time t is designated by r equals r0, its position at time 0, plus v0t, the velocity times t, plus the component that is derivable from the acceleration half of at squared. If we are interested in the position of the body, x and y, we can obtain the position by integrating the equations for Vx and Vy. X equals x0 plus v0t plus 1/2 of axt squared, and a similar equation for y. Relative velocity we have encountered previously in rectilinear motion. The relative velocity of A with respect to B is VA plus VB, and similarly the relative velocity of B with respect to A, VBA, is VB minus VA. The absolute values of VAB and VBA are the same. It's important in solving problems in relative velocity to remember the direction of the vectors as well as their magnitudes. Let's apply the motion in a plane to projectile motion. A projectile such as a ball or a cannon ball or soccer ball or a tennis ball or an arrow that's thrown up in the air is subject to acceleration due to gravity, which is ay equals minus g. For a projectile that is thrown up from the ground, where x0 is 0 and y0 is 0, the equations of motion are Vx is dx by dt, which, as is shown by the diagram on the right hand side, is the component of v in the x direction, that's v0 cosine theta. Similarly, Vy, since the velocity in the y direction is subject to an acceleration minus g, would be given by v0 sine theta minus gt. If we are interested in the positions, and once again we integrate the equations for Vx and Vy, and we obtain x equals v0 cosine theta t, y equals v0 sine theta t minus 1/2 of gt squared. Now it can be shown that a projectile that is thrown off follows a path that is a parabola given by the equation y equals ax plus bx squared, where a is tangent of theta 0 and b is minus g divided by 2 v0 cosine theta 0 squared. These equations can be derived easily by remembering the definitions of v and a and taking into consideration the geometry. I would recommend that you look over the derivation in the textbook and try to do it by yourself on a piece of paper so that you become familiar with the logic of motion of a body. Illustrated here is a parabola starting out from the origin O with an initial velocity v0 at an angle theta 0 from the x-axis with initial velocity components v0x and v0y. It can be seen that v0x remains the same as the body traverses the trajectory up at the top or as it hits the ground, whereas v0y is subjected to a constant pull downwards due to the acceleration minus g and changes during the trajectory. The questions related to time spent by a projectile in the air, as well as the maximum height, the total flight time, and the range, offer good opportunities for examiners to pose questions to you so that they can test whether or not you understand the motion of a projectile in a xy plane. When a projectile attains the maximum height, as can be seen from this diagram up at the top, the velocity in the y direction is 0, since the velocity of Vy is equal to v0 sine theta 0 minus gt. The time to attain the maximum height Tm is v0 sine theta 0 divided by g. If you substitute Tm in the equation for y, you get the maximum height Hm to be v0 sine theta squared divided by 2g. The total flight time is equal to twice the time that the object takes to attain the maximum height, that's 2Tm, and the range r is travel in time t sub f, which is twice Tm. Since the velocity component in the x direction doesn't change, that is v0 cosine theta 0 times t sub f. A few words about uniform circular motion, such as what you would encounter when you are driving on a curve or riding a bike on a curve. The angular velocity, omega, is the rate of change of the angle d theta by dt. It is a vector by vector analysis that is perpendicular to the plane of rotation. The linear velocity, on the other hand, which is ds by dt, is a vector tangential to the curve at a given point. We know from geometry that the distance ds is equal to r d theta, and therefore v is equal to r omega. When a body moves on a circle, such as shown here, a body moving from P to P prime. At P, its position is given by the vector r. At P prime, its position is given by r prime. And by vector analysis, this is v prime, the change in velocity delta v points in the direction of the center C. That gives rise to the acceleration, which is the component of acceleration in the direction of the center, called centripetal acceleration, and is determined at the rate of change of velocity. A sub c r omega squared equals v squared by r. It's a vector directed towards the center. In terms of the frequency nu, that's cycles per second, omega is 2 pi nu. That means a sub c would be 4 pi squared nu squared r. So summarily, this is a fairly straightforward chapter that defines once again a scalar and a vector addition, subtraction, multiplication, motion in a xy plane, one example of which is a projectile motion such as the motion of an arrow or a ball, and the specific case of uniform circular motion such as what you encounter in a racing car situation around a curve, or a horse racing similarly around a ring. So what we have done here is to recapitulate the vocabulary as well as the equations that we have encountered for motion of a body in the xy plane, for projectile motion in the xy plane, the parabolic path of a projectile that's thrown up in the air, and the projectile motion in the xy plane for the maximum height, the total flight time, and the range r. For uniform circular motion, omega is d theta by dt, v is r omega, the centripetal acceleration is r omega squared or v squared over r, where omega is related to the frequency nu by 2 pi nu. I would suggest that you review and be familiar with basic geometry, especially of triangles and circles. They will be of great help to you in solving problems in planar motion. For example, in a triangle with sides A, B, C and opposite subtended angles A, B and C, A over sine A equals B over sine B equals C over sine C. What we have done is to give you a synopsis of the chapter in order for you to understand the basic concepts, to cultivate critical thinking and the ability to solve practical problems in physics. It is important that you practice with actual examples from previous NEET, JEE, board, and other exams. We at rankstudent.com have provided you with almost 100,000 examples. So I would urge that you visit this site, download the examples, and practice often. Start early. Practice often. Practice helps solidify the concepts. It has been shown that people learn by listening and then doing. Merely listening is not enough. Merely doing without listening may not lead to understanding. Merely listening without doing will not give you the confidence to solve practical problems in physics. I thank you for your attention.